Cold open. The comet that blinked lasers paint the night as 3I/Atlas stutters across the sky, accelerating, pausing, then appearing a fraction of a degree ahead of itself, like a video buffering the future. Telescopes panic, chat windows explode. Someone whispers, "It just overtook its own position." Cue goosebumps, cue countdowns, cue the universe tapping the glass. If you have never watched Astronomers in Crisis, imagine librarians discovering the alphabet has rearranged itself while everyone was mid-sentence. Observatories lock onto the newcomer, computers hum, and a tiny pale dot becomes the most important speck since that smudge you swore was not on the lens. Within minutes, the first key insight lands. Our sky is not a static backdrop. It is a clock. Every light has an expected place and an expected time. When something leaps, even by what looks like a small slice of the sky, we are not seeing drama, we are seeing the schedule break. And when the sky breaks its schedule, humans invent new words for yikes. The immediate suspects are boring, which is why they are comforting. Maybe the tracking software glitched. Maybe the telescope was nudged by a gust of wind, or a raccoon with strong opinions about comets. Maybe the detector's timing got out of sync, so that the images stitched together like an album of slightly drunk selfies. But the second insight is equally quick. Boring errors repeat in boring ways. This jump does not. It is precise, measured, and repeatable enough that separate instruments in separate time zones report the same hiccup. Conspiracy theorists prepare their triumphant playlists. Scientists prepare longer checklists. Here is how a night like this actually works. You point a telescope not at the comet, but at the space where the comet is calculated to be, based on a chain of earlier measurements. Each new image gives you a pinpoint that you turn into a position on a grid mapped to the sky. Do that many times, and you get a path that can be modeled. The model predicts where the comet will be a bit later. The predictions get folded back into the pointing. It is like tossing breadcrumbs in front of a duck and calling it guidance. When the duck teleports between crumbs, you have a mystery. Either your crumbs are lying, or your duck is not a duck. Comets are notoriously messy travelers. They shed gas and dust, and the jets of material act like miniature thrusters. If the jets fire more on one side than the other, the nucleus can accelerate in strange directions. Usually, this is a slow, graceful drift. Tonight, it is a blink. Telescopes catch a brief brightening, as if sunlight flashed off fresh ice, then a faint smudge where the comet should have been, then a sharper dot slightly ahead. Someone jokes that the comet hit fast forward, another counters that the comet simply ignored the buffering icon. Space has timing, comets have a sense of humor. Meanwhile, the public sky feeds light up. Amateur astronomers drop images into group chats faster than professional pipelines can digest theirs. A teenager posts a handheld phone shot that somehow nails the moment, and suddenly 1 million people are doing parallax math without knowing the word. In control rooms, scientists quietly love this chaos. More eyes mean more data. And more data means the chance to slice the event into pieces and ask, did the brightness change first, or the position? Did different colors of light behave differently? Are there multiple components in the tail fanning out like a deck of cards? The cosmos can be shy. Tonight, it is doing card tricks under floodlights. Then there is the sound of the night, which is mostly numbers spoken softly. Someone reads a time mark. Someone else reads a coordinate pair. A third person says, again, time marks matter because telescopes do not only capture where, they capture when. If the when is off by even a blink, the where turns into fiction. That is why laser guide stars lance the sky, not only to sharpen the image through shimmering air, but to keep the ballet of mirrors and software in step. Do not blame the lasers for the comet's shenanigans. They are the metronomes. The sky is the drummer who showed up with extra limbs. By midnight, the pattern has a shape. The comet brightens. The image smears by a whisper. and the next clean frame shows it slightly ahead along its path, not sideways, not random, ahead, like it briefly became the kind of student who finishes the test, hands it in, and is somehow already across the street getting a snack. The team starts to frame possibilities that are not just equipment gremlins. Could a sudden outburst of gas create a short-lived plume that reforms the nucleus farther along? Could an icy fragment detach and flare while the main body slips forward unseen? Could the motion be a trick of perspective as the comet crosses a region of the sky dense with background stars, causing software to mistake tail for nucleus? These are not excuses. These are invitations to look closer. And yet the way the jump repeats feels different, as if the comet is keeping time with something not in the usual playlist of gravity and sunlight. The jokes turn sharper. Someone mutters that the comet just overtook its own position. Someone else says that is not how position works, then looks at the plot and stops mid-lecture. Consider how deeply embedded our trust in celestial schedules is. We plan eclipses centuries ahead. We park spacecraft on pinpoints beyond planets. We measure the drift of continents by timing pulsars. When a small body flicks the schedule on the nose, you feel it in your bones. It is like your calendar app developing an attitude. The jump becomes the kind of anomaly that changes metaphors. No longer a stutter, it is a blink. A blink suggests agency, something that happens between frames, because the universe closed its eye and opened it again. Of course, the universe does not have eyes, but the language helps us keep steady as we reach for new models. You can feel the room's mood settle into that weird mix of fear and joy that only science cooks up. Fear that we misread something fundamental, joy that we might get to rewrite a footnote in the manual. The universe rarely sends push notifications. Tonight, it sent one with all caps. Phones start buzzing with requests from journalists. There is a quick debate about how to phrase this without inviting 1,000 headlines about portals. The safest line is also the truest. We observed a comet that appeared to move ahead of its predicted position in a way not fully explained by known effects. And we are collecting more data. That sentence will not break the internet, but it will let the next hours of observing breathe, because the next hours matter. If the blink is tied to solar rotation, or to the comet's spin, or to some subtle play of thermal stresses, it will have a rhythm. If it has a rhythm, we can learn the steps. As dawn bruises the horizon, a final frame lands. The comet has settled back into ordinary, obedient drift, as if it got the silliness out of its system. People stretch, stand, and put in orders for heroic breakfasts. Somewhere between egg number 1 and egg number 2, someone says, "If the sky can blink, what else can it do?" The room laughs, but gently, because once you have seen a schedule bend, you never look at clocks the same way again. Next time, we follow the dust home and pry open the story it carries, a timestamp in ice that refuses to match our calendars. Chapter 2. The timestamp in the ice. The timestamp in the ice. In a clean room, a sliver of 3IATLAS dust reveals decay products that should have faded millions of years ago, except they look fresh. Isotope ratios read like a postcard, postmarked Jurassic. Wish you were here. The lab goes quiet. The coffee does not. Here is the first shock, delivered with the politeness of a sterile glove. Atoms keep time even when we are not looking. The key insight lands fast. Certain elements come in twin versions called isotopes. One version is stable, the reliable friend who never leaves the party. The other is unstable, the guest who quietly slips away by turning into something else. That slipping away happens at a steady pace, like a drum beat written into the nucleus. On Earth, we use those beats to date fossils, rocks, and the occasional argument. In this lab, under filtered lights and air that smells like disinfected nothing, the beats in comet dust refuse to line up with the usual song. Technicians ease the particle through a chain of instruments built to be suspicious. First, a scanning microscope maps its landscape, craters smaller than a bacterium, glassy patches, delicate whiskers of carbon built by star forgers long before our sun found a name. Then a laser plucks atoms out and passes them to a mass spectrometer, a device that sorts by weight the way a librarian sorts by genre. Heavy daughter products show up where light parent isotopes should have been. But more baffling is the ratio between them. On paper, the mix says the parent should have had many millions of years to fade. In the dust, the parent looks barely aged, like a vampire at a high school reunion. Cue the checklist. Could sunlight in space have tampered with the counts? High-energy particles do nudge atoms in unhelpful ways. But the dust grain carries a rind, a thin glass coat baked by solar heat that should have recorded those insults. The coat is intact, with damage marks that scream normal space weathering, not a full nuclear spa day. Did the instruments misread the masses? The team runs standards, then runs them again. The machine hums the same answer back. Your numbers are fine. Your universe is weird. A geochemist sketches the story of radiometric dating on a whiteboard, because when reality misbehaves, we go back to bedtime stories. Imagine a jar of sand where black grains slowly turn into white grains at a known pace. Count the ratio, and you know how long the sand has been sitting. Our grain of comet dust is like reaching into the jar and finding black grains that should have already become white, except the surrounding white grains insist they have seen plenty of time pass. It is as if different parts of the same jar kept different calendars. Now the clean room turns theater. People move with the hush of a library where all the books recently learned to talk. One scientist peers through the glove box window and murmurs, "Do not sneeze near my paradox." Another lines up backup samples so neatly that the bench looks like a parade ground for specks. The grain is sliced again with a diamond knife, thin enough to make an onion cry. Cross-sections reveal layers, like tree rings carved by freezing and thawing. Each ring can be dated by a different isotope pair, a clever trick in the geochemist's toolbox. The rings do not agree. The inner core looks primordial, older than the oldest mountains on Earth, while a middle ring behaves like it formed during the age of dinosaurs, and an outer frosting reads as young as civilization. The dust is a nested set of clocks that never met. Explanations line up like suspects in a mystery novel. Perhaps the comet spent time near a giant planet whose radiation belts cooked the outer layers, but spared the inner core. Maybe micrometeorite impacts heated only certain rings, resetting their atomic clocks the way a power outage resets your microwave timer, but not your wristwatch. Or maybe the comet visited a region of space where ionizing particles are unusually well behaved, preserving parents that usually decay faster. Each idea wins a moment of applause and then collides with some inconvenient measurement. The damage tracks are wrong for a planetary sauna. The melt patterns do not match impact, reheating alone. The preserved parents are nestled beside daughters that should not be there if the whole neighborhood had been quiet. Enter the technique with the delightful name Noble Gas Mass Spectrometry, which sniffs tiny whispers of helium and neon hiding in pockets inside the grain. These gases are escape artists. Given heat or cracks, they vanish. Yet here they are, trapped like shy party guests. Their amounts point to long periods of deep cold with sudden, sharp, warm episodes. Picture a freezer that is mostly reliable, but occasionally thinks it is a toaster. Those episodes could reset some isotopic clocks, while leaving others snoozing. But the timing is the kicker. The episodes line up with ages that echo events in early solar history, and then jump to ages that resemble much later epochs. It is as if the dust grain had been archived in multiple eras and stamped by each. The room's mood shifts from confusion to curiosity, with better posture. If time is a story told by atoms, then this grain has been edited by an unusual author. One researcher floats a possibility so gentle you could miss the audacity. Perhaps the grain spent time shielded inside a larger, icy matrix, then was released, then reburied, moving between layers that were themselves assembled at very different times. A comet can be a patchwork quilt. If that quilt was stitched in a place where material from different ages mingled without fully mixing, say a quiet nursery in the outer reaches, then the clocks could disagree without breaking physics. The oddity is not the disagreement, it is the precision with which each layer keeps a memory of its separate life. To test that, the team aims a beam that can measure atom by atom across a micrometer highway. The profile reads like a travel diary. Ancient core, untouched by recent mischief. Middle ring, reheated just enough to jog one clock while leaving another asleep. Outer rind, exposed to solar breath in what looks like recent centuries. The coffee machine hisses a scent. Someone writes on the lab board, a fossil that remembers more than one past. Someone else adds, and maybe more than one neighborhood. By evening, the paradox has softened into a map. Not a neat one, more like a coastline traced by a nervous hand, but a map all the same. The timestamp in the ice is not a single date. It is a stack of dates from places that rarely share company. That stack hints that our visitor is not simply old, it is complicated. Like a museum exhibit that has been remodeled so many times that the floor remembers a castle, while the ceiling swears it grew in a spaceship. Next time, we will leave the lab and head to the archive of the sky itself, chasing whispers in ancient charts and oral maps to see whether history caught this wanderer before, and what it wrote down when it did. Chapter 3, History's Phantom Trail. History's Phantom Trail. Old star charts from Polynesian navigators and Babylonian tablets show a double-tailed wanderer that matches 3I/Atlas's weird loop. Only the dates are centuries apart. The same comet signature, like a signature that forgot what year it is. Libraries become launch pads. The hunt begins not under a dome, but under a desk lamp, with scanned pages, clay impressions, and notes that smell like long conversations. You would think a comet lives only in the sky, but it also hides in margins, chants, and ledger lines. The first clue is a phrase scratched into a cuneiform tablet, a hairy star that turned like a fish and lifted a second tail. The tablet keeps time with lunar months and royal reigns, which is adorable and chaotic, like telling you the Super Bowl occurred during the reign of the uncle who owed me a goat. Still, there it is, a two-tailed visitor that appeared, hesitated near a known constellation, then curved oddly before vanishing. A librarian circles the lines in pencil the way a detective circles footprints in dust. Across an ocean and many centuries in method, Polynesian wayfinders kept astronomy alive in songs and star compasses, carried in their heads. Their charts were not paper, but memory. Their ink was breath. In transcriptions recorded later, there is a chant about a traveler with two spears of light that leaned apart like a forked wave. The chant ties that appearance to a month defined by a particular star rising just before dawn and to swells moving from a quarter not usual that season. There is no sketch, but there is geometry in the words, a double tail, a bend in the path, a timing that anchors it to the rhythm of ocean and sky. If this sounds like trying to reconstruct a crime with two witnesses speaking different languages and calendars, you are right. But we have the world's most patient interpreter, the sky's slow drift. Over centuries, star patterns slide with procession, like a grand clock hand, making a long, lazy circuit. If you can decode which stars the text meant, you can roll the heavens back and ask where a comet would have been seen from those islands, and where from those river valleys. The work is part astronomy, part anthropology, and part detective novel with footnotes. Babylonian notes are precise in their own way. They loved lists and omens, and if a star misbehaved, they took minutes like dedicated stargazing bureaucrats. One tablet describes a wanderer that brightened, grew a second tail of paler light, then seemed to hesitate near the horns of a familiar constellation before taking a path that curved southward sooner than expected. Another mentions a color split, a yellowish fan, paired with a faint bluish spear. That pairing is the calling card of two different tales, one of dust pushed by sunlight, one of gas dragged by the solar wind, slanting apart like two arguments at a family dinner. The angle between them, if drawn from the descriptions, is unusual, not wrong, just memorable. Over in the Pacific Archive, a missionary's notebook preserves a navigator's account of a twin-tailed light that rose at an unfamiliar bearing after midnight, then seemed to stall and jump, as if the sea itself tilted the stars. The navigator marks the bearing relative to a known zenith star and to a canoe path between islands. Convert that into the modern map of the sky, correct for latitude and the era's star rise positions, and you get a path that kinks in a spot suspiciously close to where our modern visitor does its little loop-de-loop. The count's timing, however, belongs to a century that does not match later Babylonian dates. The trail shivers like heat above a road, so the team builds a cross-cultural Rosetta Stone of sky references. Constellations become their older cousins. Month names become the nights relative to the appearance of seasonal markers. Ocean swell directions become proxies for wind belts and, indirectly, for the clarity and azimuth of dawn observations. It is far from perfect, but patterns start to peek through like shy ghosts. Where the Babylonian notes say the tail doubled and the path arced prematurely, the Polynesian chant says the twin spears leaned apart and the traveler turned early. Different poetries, same geometry. Now the fun part. Elimination by personality. Comets have styles. Some glide with grand, slow sweeps. Some erupt like popcorn. A few carry dust tails that flare wide and ion tails that behave like steel needles, snapping and reconnecting as they cross magnetic highways. The ancient descriptions match a personality profile of a comet with a flamboyant dust fan and a nervous gas spear, plus a habit of apparent hesitation, seen from Earth as a small loop or kink in its path, when geometry between Earth, comet, and Sun plays a trick. The loop is not common. It happens when we are changing our vantage point quickly, and the comet's own motion adds a curl to the plot, a celestial cursive letter tucked into the line, but the dates refuse to shake hands. The Babylonian sightings cluster around one set of years. The island accounts cluster around another, separated by centuries. Either multiple comets share a rare flair for double tails and loops, or the same traveler signed the sky in two far-apart chapters. The library becomes a test bench. We examine the ink composition of later copies to weed out scribal echoes. We look for independent weather notes, volcanic dust, unusual sunsets that might have amplified or muted tales. We even check court records for sudden decisions tied to ominous skies, because humans, bless us, schedule history around comets when we can. Then a statistical whisper comes through the noise. If you combine the angle between tails, the reported colors, the apparent bend near a specific star group, and the rate of brightening relative to lunar phase descriptions, you get a fingerprint, rare enough, that 2 or 3 separate comets would be a stretch. The overlap is not definitive, but it is uncannily neat. Imagine finding 2 signatures with the same flourish on the letter R and the same coffee stain in the corner. Either our universe has a forger, or our wanderer has been here more than once on a schedule that ignores our expectations. No one declares victory. Historians prefer cautious verbs. But the archive room hums with a new idea. Maybe some travelers keep time with rules we do not yet write in almanacs. The phantom trail is not a straight line. It is a dashed line, a breadcrumb path laid across centuries that invite us to follow. It pushes us to expand what counts as evidence, not just photographs and spectra, but stories carved in clay and sung under stars, each a unit of data with a human accent. And so the trail points forward, not to a date, but to a puzzle. If a path repeats without a period we can name, what on earth or off it is bending the schedule? Next time, we aim the simulations at that kink and ask whether space-time itself is quietly curtsying, the orbit that bends calendars. Chapter 4. The orbit that bends calendars. The orbit that bends calendars. Simulations refuse to close. The trajectory only makes sense if space-time does a small curtsy near perihelion, not a warp drive, more like a pothole in time. Astronomers rename their whiteboard plot device, then realize it is not a joke. The first key insight lands before the coffee cools. The equations that send spacecraft to distant worlds are not merely good. They are rude about how good they are. Feed them a comet's positions, and they reward you with a tidy path that threads months of sky like beads on a wire. But run the same machinery on our blink-happy traveler, and the wire keeps kinking at the same place, the closed swing around the sun. Tweak the initial conditions. Extend the time span. Swap numerical solvers. The kink survives like a rumor with a gym membership. To understand the problem, picture how an orbit is normally stitched. You start with images that pin the object against the background stars, then correct them for every trick light plays on its way to your detector. The motion of Earth around the sun, the motion of the observatory on the spinning Earth, even the tiny time a photon spends crossing the solar system. Then you hand those clean waypoints to a simulator that includes the gravity of the sun and planets, the pressure of sunlight, and the faint tug from outgassing, if you have measurements for that. Usually, the simulated ribbon threads right through the real points. Here, the ribbon glides beautifully until the comet nears the sun, where the path needs a nudge in the timeline to match reality. Space is not pushing it aside, time is. So the team performs the ritual of humility. Add the corrections you assume are too small to matter, then watch them matter. They turn on the relativistic precession that nudges the orbit of Mercury and should slightly adjust any close solar swing. They account for the way light passing near the sun takes a longer route through curved space-time, which changes the exact moments when observations should be stamped. They include tides from the planets in case a distant giant is participating. By whisper, the fit improves, but not enough. The pothole remains. It is as if the clock that the orbit listens to runs slow for a breath, then resumes. Enter the timekeepers, not wristwatches, but pulsars and atomic standards that underpin observatory timing. If the issue is a misread clock, it will reveal itself by mismatched stamps across different facilities. Instead, the discrepancies align. Independent observatories see the same need to bend their predicted times near perihelion. The problem does not live in the instruments, it lives in the model of the path itself. That is when someone writes plot device in big letters, and no one laughs as loudly as usual. The next move is counterintuitive. Stop thinking of the comet as a dot, and think of it as a traveler whose own experience of time might be fractionally different during that fierce solar close pass. Gravity slows clocks. That is not a metaphor. It is a measured fact. Close to the sun, time for the comet would tick a hair slower than for a clock far away. We already include that hair in standard calculations, but the data are asking for a slightly thicker hair, like finding out your ruler shrinks by a whisper when you bring it near a campfire. Not much, just enough to make the sum come out right. What could add a whisper of extra slow time? One conservative thought. Perhaps the comet dips through a region of unusually concentrated solar mass, not because the sun suddenly gained weight, but because the path crosses a valley. In the way, mass and pressure inside the sun curve space-time. The sun is not a quiet orb. It throbs and rings with waves. If those internal motions subtly reshape the gravitational landscape along the precise corridor the comet takes, you could get a momentary extra sag in the time fabric. Our pothole, another cautious idea. During the swing, the comet's own extended cloud of gas and dust briefly increases the effective cross-section that interacts with solar radiation and magnetic fields, altering how we infer its position from the light we receive. That would masquerade as a timing shift without actually being one. The team models both and finds each explains part of the kink But neither earns the crown. When physics hesitates, computing pounces. They roll out a suite of integrators that adapt their step sizes like mountain goats. Nimble near steep slopes, relaxed on flats, they inject mock data with known properties to test whether their tools can invent potholes from numerical quirks. They cannot. They add a machine learning layer trained to absorb the messiness of solar wind variations and thermal lag in the nucleus, then fold its learned nudges into the classical dynamics. The hybrid model reduces random scatter and leaves behind the same stubborn, coherent time dip at perihelion. It is the simulation equivalent of dusting for prints and finding the same thumb on every doorknob. Here is where the room's mood changes, from concerned to curious with an edge. Suppose the pothole is real, a local, lawful feature of the corridor the comet travels. It is not a portal or a science fiction freeway. It is more like the way sound bends over hot asphalt, except the asphalt is space-time, and the bend tweaks timing rather than pitch. That does not break the universe. It decorates it. The practical consequence is startling. If such dips exist along certain close solar arcs, then a small family of objects could periodically inherit a tiny phase shift in their orbits, arriving a little early or a little late compared with what clean equations predict. Over decades, that phase shift would add character to their sky signatures. Over centuries, it would become a calling card. The team drafts a proposal that reads like a dare to nature. Observe other sun grazers with absurdly precise timing, not only where they are, but when their brightness pulses line up with rotation. If the pothole is a genuine time sag, those pulses should bunch up in a telltale way during the close pass, then relax afterward. There is also a spacecraft idea, penciled in the margins, an escort that flies just far enough from the comet to share the same corridor, but not the same dust, carrying a clock that compares its own heartbeat with a distant standard in real time. If the corridor curves time, the escort will feel the dip too. A pothole test with a dashboard cam. If all this sounds like astronomers inventing budget requests with poetic metaphors, fair, but the numbers are sober. The orbit that refuses to close is not flailing, it is pointing. It asks us to refine how we fold the sun's inner life into the space around it, and to respect that time is not a wallpaper we can peel and flatten at will. Time has topography. Most of the map is smooth. Some of it has gentle hills. And a few places, just near the fire, have dents you only notice if you roll a marble right through them. Next time, the dents spill out of the lab and onto late-night television. We leave equations for punchlines and see what happens when a quiet time pothole meets a loud planet. Public Panic, Cosmic Comedy. Chapter 5. Public Panic, Cosmic Comedy. Public Panic, Cosmic Comedy. News anchors ask if we should buy canned beans or quantum helmets. Conspiracy forums sell both. A late-night host quips, finally, a visitor that respects no time zones. Somewhere, a child draws a crayon timeline with a loop and labels it home. The story leaks from observatories into living rooms with that strange velocity only Big Sky News has. Morning shows run graphics of a very dramatic comet squeezing past a very nervous sun, while an expert tries to say the words small effect and local phenomenon between chirpy weather updates. The tagline beneath her reads, "Time, wobble?" in a font usually reserved for sports finals. Viewers sip coffee with the same expression used for roller coasters. This seems fun if it ends where we started. Retail senses its moment. A startup debuts a sleek headpiece shaped like a retro hairdryer and calls it a temporal safety device, promising it will keep your personal schedule aligned with reality. It is basically a hat that weighs like regret. Influencers unbox it, tap the shiny surface, and declare themselves future-proof. Meanwhile, a hardware store runs a practical ad. Beans, batteries, and a friendly reminder that if time gets bumpy, flashlights still help. Sensible marketing is the real superhero cape. Then comes the internet chorus. which is equal parts chorus and circus. A cooking channel posts a recipe titled Chronological Stew and claims it tastes better if you prepare it tomorrow. A history meme page edits famous portraits so that everyone glances a few inches to the left, with captions about arriving early for your own selfie. The comments do what comments do. They invent lore, they debate law, and occasionally they land on something sincere, like a nurse saying night shifts already mess with time. Thank you very much. Government briefings follow, delivered at podiums that look designed to withstand awkward questions. Officials reassure the public that there is no evidence of danger, only the need for more study. A journalist asks if school start times will change due to wavy minutes. The official pauses long enough for every parent watching to whisper please. A science advisor translates, "The cosmos sometimes has wrinkles. Your bus schedule does not." The nation exhales with a noise like a balloon, deciding to behave. Markets react in that allergic way. Markets have to new vocabulary. Companies with anything even vaguely clock-shaped in their logo see a sudden uptick. A watchmaker trends, not because anyone thinks a wristwatch can outstare the sun, but because people like symbols you can hold. Toward closing bell, an anchor declares that time remains a reliable growth sector, which is both nonsense and comfort. Investors do not mind a paradox if it does not ask for a receipt. In classrooms, teachers lean into the moment. A physics teacher draws a racetrack and places a toy car near a heat lamp to explain that speed and gravity can make clocks do interesting stretches. A student asks if homework will arrive before it is assigned. The teacher smiles and says that has never happened in recorded history. In art class, the crayon timeline with a loop earns a gold star and a place on the wall. It is a fine first map of wonder. The comedy circuit goes to work. Jokes arrive like meteors, light, fast, and occasionally leaving tiny craters of truth. One late-night host says the comet was early, which makes it more punctual than his cable installer. Another wonders if this is the year we finally agree to stop arguing about daylight saving because the sun just played a better prank. Laughter does what it always does in the face of cosmic strangeness. It keeps the floor from tilting. Not everyone is laughing. Forums sprout diagrams drawn with red lines connecting absolutely everything. A thread insists that the jump in the sky is proof of a secret agency that edits time on weekends. A reply claims that is absurd, because editing time would obviously require weekdays. Moderators delete the truly wild claims and pin a fact sheet. Long arcs of space can subtly change how clocks tick. Nobody is erasing birthdays, and if you see a link selling crystal hourglasses for protection, please log off and drink water. The crystal hourglasses sell out anyway, because humanity is a collage of caution and curiosity with a coupon. Amid the noise, a quiet movement blooms. Amateur observers organize sky nights, not to panic watch, but to learn. Parks fill with blankets and thermoses. People trade focus tips and point out constellations, like old friends who have not changed their hair in 1,000 years. A kid asks why the comet seems to pause near one star and then glide on. The answer is a neat sentence about perspective and motion that lands better under starlight than under studio lights. When the comet finally sidles across the frame, a cheer goes up that is part sports, part prayer. Museums jump in with pop-up exhibits. One hall becomes a timeline you can walk, with floor lights that speed up and slow down to mimic how gravity nudges minutes. In a corner, a booth asks visitors to record what they would send their earlier self if they could. The messages are mundane and lovely. Remember sunscreen, call your grandmother, say yes to the trip. When cosmic news rattles us, we inventory our small, real clocks. Scientists, for their part, hold community Q&A sessions that are equal parts classroom and therapy. They explain what models can and cannot do, where confidence lives, and where curiosity gets the keys. Houseplants on the stage soften the mood. Someone asks if pets can sense time hiccups. a biologist talks about circadian rhythms and hunger cues, and how cats already believe hours are suggestions. The room laughs, and then the questions turn to the heart of it. Are we safe? Are we seen? Is the future still mostly ordinary? The answer is yes to all three, with the caveat that ordinary is a miracle we often forget to celebrate. By the end of the week, the frenzy cools into a cultural hum. The quantum helmets become paperweights, the bean shelves restock, the crayon loop dries on a refrigerator door, where it will confuse a babysitter months from now. The comet keeps moving. And we keep doing what we do after a collective double take. We fold the weird into our stories and get on with making dinner. Next time, we leave the bright lights and return to the instruments, peering at the comet's own belongings. Inside its glow, the chemistry reads like mixed luggage from different centuries. Fingerprinting tomorrow. Chapter 6. Fingerprinting tomorrow. Fingerprinting tomorrow. Spectroscopists find molecules that should not coexist. Heat-scorched organics next to pristine primordial grains. It looks like luggage packed in a hurry from different eras. The comet is a carry-on with security questions. The first key insight lands as a picture made of soundless music. Each molecule sings a private tune when light passes through or bounces off it, and spectroscopists are the people who know the lyrics. Point telescopes at the coma and tail, spread the light into a rainbow, and you get barcodes where certain colors go missing or glow brighter. Those lines spell out who is there and, just as importantly, who should not be standing next to whom. Tonight, the rainbow reads like an awkward seating chart. Fragile ices that hate warm weather sitting shoulder to shoulder with crusty, heat-baked organics that only form after long toasting. It is the space equivalent of packing both snow boots and a beach umbrella for the same afternoon. Ground arrays and orbiting observatories divide the job like a band with perfect harmony. One instrument listens to the deep infrared, where molecules stretch and bend, revealing long carbon chains and ring-like organics that usually require slow cooking on warm dust. Another watches the ultraviolet, where gases freshly kicked from the nucleus shatter and fluoresce, a telltale that icy pockets are venting in real time. A radio dish tunes into rotational notes that tell you how fast the molecules are spinning. Here is where the second insight bites. The spins whisper a chilly story, while the stretches shout a warmer one. It is as if the molecules' bodies are relaxed, like they came from a freezer, but their limbs remember yoga class. 2 thermometers, 1 object, different answers. What could make a chemistry set this contradictory? Consider the nucleus as a city of caves and ledges rather than a smooth snowball. Sunlit faces bake, shadowed alcoves nap. Jets burst from narrow vents, launching pebbles and dust grains that were hidden away for ages. Some grains leave with coats of delicate ices still clinging. Others tumble through sunbeams long enough to caramelize. The mixture collides in the coma, where our spectrometers sample a soup cooked by 2 chefs at once. A lab tech calls it a buffet, where the salad is still growing and the dessert is already burned. Accurate, if unappetizing. To stress test the story, the team watches how the spectrum changes across hours. As the nucleus rotates, one hemisphere swings into daylight. The ultraviolet signatures of fresh gas surge. The infrared glow of baked organics blooms a few minutes later, as if the dust needed time on the grill. Then, unexpectedly, a patch of spectral lines associated with very delicate ices brightens right after a hot flare. That should not happen. You do not open your freezer by pointing a hairdryer at it, unless the hairdryer knocks loose a block that immediately dives into shade. The geometry of vents and cliffs can do exactly that, jetting something free from a hot spot, only to let it sail into shadow, where it survives long enough to be measured. There are stranger hints hiding in the fine print of the lines. Some complex organics show a pattern typical of slow surface reactions on warm grains. Think of dust acting like a tiny kitchen counter, where sunlight patiently rearranges atoms over years. Next to them, you find equally complex species that, in labs on Earth, prefer to build under deep cold with the help of radiation nudges. Both sets appear together, without the usual in-between steps. The comet's packing list includes both sunscreen and snow boots because parcels of material bypassed the expected layovers and met for the first time mid-flight. Analysts run through the skeptic's playbook. Maybe our instruments mixed light from different regions. The team narrows the apertures and repeats the scan on substructures in the tail. A jet here, a fan there. The odd pairings persist, neatly localized. Maybe Earth's atmosphere added a trick of its own. Space telescopes confirm the same fingerprints above the air. Maybe we mislabeled the lines. Cross-checks with lab spectra and multiple instruments strip that excuse away too. The luggage mismatch is real. Then comes a clue with personality. Certain emission features pulse in sync with the nucleus rotation, but the pulses arrive a heartbeat earlier than the visible jet they are tied to. The explanation is deliciously messy. Charged dust and newborn molecules can surf magnetic fields and electric charges in the coma, taking a shortcut to the detector, while the heavier dust follows a slower arc. The shortcut lets freshly freed, fragile species arrive on cue with more seasoned, sun-tanned particles. Two sources, one spotlight. Back in the lab, researchers try to recreate microclimates on a chip. They press grains into porous matrices, freeze them solid, and heat one side with a lamp while zapping the other with simulated solar wind. Sensors just micrometers apart report wildly different histories. One pocket acts like a refrigerator, the next acts like a toaster on a dare. Blow gently, and you loft a mix that looks uncannily like the comet's spectrum: cold-loving molecules, hot-tempered organics, and a dust population wearing both frost and scorch marks. The conclusion is not that the comet has magic chemistry. It is that the architecture of pores and ledges makes weather at the scale of sand. Zoom out, and the portrait becomes almost tender. This traveler is not a single recipe. It is a sampler platter from many kitchens. Some ingredients formed in the deep freeze beyond giant planets, steeped in radiation that stitches simple pieces into complex threads. Others baked nearer the sun, perhaps during past close passes, when crusts darkened and sugars cracked. When gas vents sneeze, the pantry dumps its shelves into the same mixing bowl. Spectroscopy simply reads the label, while everything is still mid-air. Of course, one hypothesis sits in the doorway, like a quiet cat. What if the reason these eras meet is not only geology and sunlight, but timing itself? If certain close passes near the sun nudge the traveler across small time sags, then its pantry might be stocked from moments that do not line up on our neat calendar. That idea will need its own stage and a sturdier microphone. For now, the headline is simpler and weirder. This comet carries tomorrow and yesterday in the same pocket, and light tattles on both. Next time, we will give that pocket a name and a mechanism, sketching the notion that some icy bodies can store temporal stress, the way coral stores ocean history. The Paleoclock Hypothesis. Chapter 7. The Paleoclock Hypothesis. The Paleoclock Hypothesis. A fringe idea goes mainstream. Certain comets can become paleoclocks, storing temporal stress like coral stores ocean history. Under specific solar tides, they slip along closed, tiny time eddies. The math is ugly. The metaphor is gorgeous. Start with the picture, not the equations. Picture a layered ice rock tumbleweed with caves, pores, and veins of dust. Every time it swings near the sun, it feels tides not just in space, but in time. The way a shoreline feels the pull of the moon and leaves rings of driftwood that remember high water. A paleoclock is that shoreline, except the rings are isotopes, trapped gases, and baked crusts that hold a record of when the object felt the strongest tug. The radical twist is that the tug is not only a push or a pull, it nudges how fast moments tick for the traveler during the tightest part of its path. Time does not rip, it wrinkles. The comet keeps the wrinkle like a pressed leaf. How does an ice ball learn to keep time? Not with gears, with cycles. Imagine a nucleus that rotates so that the same scarp faces the sun right at closest approach. Heat rushes into that neighborhood, gas erupts, dust lifts, and then everything cools again. Do this pass after pass, and the architecture evolves toward a resonant routine. In that routine, microscopic layers open and close like lungs. Some layers trap noble gases, others vent them. The timing of those breaths becomes phase-locked to the orbit. If gravity makes clocks run a hair slow near the sun, these breaths align with the slowest tick, capturing a faint imprint of that difference, the way tree rings capture a drought. Now mix in the subtlety. The sun is not a metronome. It hums, it flickers, it spits storms. When the internal waves of the sun and the spin of the comet line up just right, the corridor the comet flies through can have a slightly different curvature of time than the average. Not a tunnel, not a shortcut, just a shallow eddy. A loop where a small parcel of the traveler's history gets folded back on itself by a fraction of a heartbeat. Most objects skate over that ripple and forget it. A paleo clock remembers, because its layers and vents are already tuned to catch rhythms. It is like a choir that suddenly hears a new harmony and adds it to the song. What would a paleo clock do that a regular comet would not? It would carry mismatched ages in close quarters without chaos. You would find fresh-seeming isotope parents next to veteran daughters. And both would be right, because one layer kept a slower beat during specific perihelia. It would show a rotational light pulse that bunches ever so slightly during the tight swing and then relaxes, a fingerprint of the beat change rather than mere geometry. It would also throw off jets that arrive a blink earlier or later than expected, as if the vents themselves obey a calendar with occasional elastic days. Space does not issue punch cards, but the ice acts like it has one. The phrase temporal stress sounds like a coffee shortage in a physics department, but here it means something quiet. Different parts of the same body experiencing time at slightly different rates during a cycle, then being locked together again by freezing, sintering, and the collapse of porous walls. The freeze-thaw cements the differences into the fabric. Over many orbits, the object becomes a palimpsest of ticks and tocks from multiple seasons of the sun. That is why coral is such a useful metaphor. Coral does not make tides. It records them in a skeleton of subtle bands. A paleo clock does not make time eddies. It imprints them in layers of ice and dust. Skeptics ask the healthy questions. Could all this be explained by ordinary heating and outgassing? Much of it, yes. Thermal physics is a generous host, but the paleo clock idea earns its seat if it predicts more than it retells. So it makes testable promises. Promise 1. During the closest approach, high-speed spectroscopic sampling should find that very delicate molecules spike at phases that are slightly ahead of the thermal curve, as if a memory cue triggered venting before the sun did. Promise 2. Isotopic ages across micrometer scales should cluster into bands whose spacing matches the object's orbital period, but with occasional offsets that cannot be explained by seasonal shadowing alone. Promise 3. A second object of similar path and spin should show the same style of offsets if it shares the corridor. A third that misses the corridor should not. How would you catch a paleo clock in the act? Fly an escort clock. Not a wristwatch, but a small craft with a reference oscillator that talks to a distant standard and keeps notes during the swing. If time's pace shifts along the corridor, the escort and the ground clock will disagree by a whisper that lines up with the comet's closest approach. At the same time, map the jets with fast imaging and tag their pulses. If those pulses squeeze together slightly during the dip, you have a chorus of evidence. The ice, the gas, and the clock all humming the same measure. Laboratories can rehearse on miniature stages. Take porous ice analogues seeded with dust. spin them in a cold drum, heat them with a lamp on a controlled schedule that mimics a sun grazer's day, and cycle the schedule with small tweaks to the timing. If the sample evolves pockets that vent earlier than heating would normally dictate, you have a mechanical memory, the lab cousin of a paleo clock. Add radiation that opens and heals pores, and you can train the sample to a rhythm. When the rhythm shifts, see whether it keeps the old beat for a while, then snaps to the new. That snap is the signature of a clock that stores stress. None of this requires bending causality or borrowing science fiction. It asks us to accept that clocks are not only devices on desks, they are patterns in matter that respond to rhythm. If comets can learn a rhythm, they can keep it. And if a corridor near the sun teaches a rhythm that includes slightly slow ticks, a small company of travelers might return carrying those ticks in their bones. The math is a snarl, because nature likes curvy lines. The metaphor is gorgeous, because it gives us a way to point and say, their time left a fingerprint. Next time, we try to listen for that fingerprint as a real signal in space, a faint whisper ahead of the traveler, like thunder arriving before lightning, the echo that says the beat is about to change. Chapter 8. Listening for the echo. Listening for the echo. Radio arrays hunt for a faint time, static ahead of 3IATLAS's path. Like thunder arriving before lightning, they find a whisper that should not be there, an echo from the object's next position. The future hums. Humanity leans closer. The first key insight arrives as a plot that should be empty. Radio astronomers line up dishes across deserts and valleys, link them by fiber, and make one Earth-sized ear. They point not at the comet's bright tail, but at the patch of sky it will sweep through a little later. That patch twitches, not loudly, not in a way you would hear on a speaker, but in a pattern that matches the comet's own radio flutter, with a shift that leads rather than lags. In plain terms, the static ahead of the traveler already knows the traveler's song. What song is that? Comets murmur on radio bands in several voices. Dust and gas interact with the solar wind, which crackles like dry leaves. Charged grains flicker as they tumble. The tail can act as a loose wire in a giant circuit, modulating background hiss. None of this is news. What jolts the room is that the hiss in front of the path carries a fingerprint that should only appear after the nucleus arrives and starts stirring the plasma. It is as though footprints appear in the sand before the walker steps there, faint and wind-blown, but unmistakably in stride. To make sure the sea is not fooling the sailors, the array team runs the classic test, correlation. They take the radio flutter measured at the comet's current position and slide it along the time axis to see where it matches the flutter from the patch ahead. Instead of finding a match with a delay, they find the best match with a small lead. It is a negative echo, a preview. Engineers stare at the screen with the same expression used for magic tricks and spilled coffee. Then they do the unglamorous work of ruining their own discovery. They check clocks, cables, calibrators, and code. The preview does not go away. If this were a simple reflection, the physics would stomp in and complain. Nothing outruns light. Good, because nothing is. The effect lives in the medium, not in the mailman. The solar wind is a river of charged particles braided with magnetic fields. Every eddy and filament travels with its own speed and memory. If the comet drags and warps this medium during each rotation, it leaves behind a pattern that is carried along the field lines. Think of leaves on a stream learning the shape of a passing oar and relaying that shape downstream before the boat's hull arrives. In space, the directions are trickier, and downstream can curve weirdly, but the idea holds, the medium can gossip. Map makers get to work. They trace the direction of the magnetic field around the comet's path using polarized radio signals from distant quasars that shine through the region. Those signals twist as they pass through the charged sea, revealing the orientation of invisible scaffolding. The twist lines point from the comet's current location toward the blank patch that twitched Drawn together, these lines sketch a corridor where information about the comet's activity can surf the field ahead of the nucleus, like a rumor on a group chat. The rumor has grammar. The preview is not a copy of everything that happens near the nucleus. It carries specific beats, a rise and fall that matches the rotation period, a faint sideband that tracks a jet turning on and off, and a softening whenever the comet faces away from the sun. In other words, it knows the chorus and a couple of verses, but not the bridge. That makes sense if the preview is written by the medium remembering average behavior, rather than recording every fresh sneeze of gas. The future is not arriving early. The recent past is being projected into the path ahead. To be sure, the team tries a brutal experiment with data. They shuffle the measured time series into segments, hide some segments, and challenge their algorithms to predict the next part using only the preview channel. The prediction beats chance and even outperforms a model that uses geometry and heating alone. That is not prophecy, it is weather. The plasma weather in front of the comet is preconditioned by the comet's own previous passes through nearby space and by the steady rhythm of its vents. The array is not hearing the future, it is hearing the tracks of yesterday that the river is delivering to tomorrow. Not everyone is convinced. Critics point out that the solar wind is restless. Maybe a distant eruption on the sun launched a wave that looks like the comet's rhythm and happened to pass in front first. The array counters by comparing many days. The preview persists when solar conditions vary. It drops when the comet's rotation slows a little, then returns with the new beat. Coincidence does not keep time that well. Another suggestion is that the instruments are picking up radio chatter from Earth that sneaks along side lobes in a way that mimics the lead. Engineers grin, the tired grin of people who have chased ground interference since the dawn of antennas. They move the observation to a different array under a different sky. The effect follows the comet, not the parking lot lights. One clever test cements the mood. The team watches a background pulsar, a cosmic lighthouse that flashes at a precise tempo, while the comet passes nearby on the sky. The pulsars do not change in arrival time, but their tiny shape wiggles exactly when the preview channel wiggles, as though the pulsar's beam passed through wrinkles in the medium that already carry the comet's accent. The lighthouse shines steady, the air in front of it hums with a familiar tune. This is not a loophole in causality, it is a new kind of forecast. The comet sculpts the space around it, and flowing fields transport that sculpture slightly ahead along the path. Radio arrays, exquisitely nosy, can read those transported shapes the way you read ripples to know a boat is coming around the bend. The practical payoff is delicious. If you can hear the corridor sing before the nucleus arrives, you can plan where to look, when to look, and what hazards a spacecraft might meet. You can even test the paleo clock idea by checking whether the preview grows stronger during the tightest part of the orbit, when time runs its slowest and rhythms lock the hardest. Somewhere far from the consoles, a child puts a seashell to an ear and hears the ocean. Radio astronomers do the same with the sky and hear tomorrow's weather in the wind. The future does not call collect, it rustles. Next time, we stop only listening and start packing hardware. Agencies sharpen pencils, raid snack drawers, and sketch an audacious plan to tag the traveler with beacons. Mission Scramble. Chapter 9. Mission Scramble. Tag the comet. Mission Scramble. Tag the comet. Agencies fuse budgets with duct tape and caffeine. Plan, fast intercept, sample, and a string of micro-beacons to ride the time eddy. Engineers joke that the schedule is impossible. Management says perfect. It matches the theme. The first meeting happens at the dangerous hour when everyone is still optimistic. A whiteboard fills with arrows, then more arrows, then a doodle of a comet wearing a hard hat. The essentials crystallize quickly. We need a craft that gets to the target before its next close kiss with the sun, skims the coma without being sandblasted, grabs a pinch of material, and then seeds the path with breadcrumbs that can feel the same temporal tug the comet feels. Someone asks for a reasonable timeline. The room laughs in fluent panic. Speed is the first bully in the hallway. Comets do not wait, they sprint. A heavy flagship would arrive fashionably late, so the team pivots to a bruiser in a runner's body, a compact bus with big attitude. Propulsion gets a grab bag approach, high thrust to jump off the line, then efficient ion engines to stretch the sprint into a marathon. A launch window shows up like a shy guest, tight but not imaginary. If we miss it, the next one is worse. And by worse, the flight engineer means the sun becomes a magnifying glass, and we are the ant. Thermal reality slaps next. Near the sun, the spacecraft will bake and shed radiance like a pizza oven on a joyride. Traditional heat shields are heavy, so the materials team proposes a layered sunshade that acts like a stack of mirrored postcards. It folds out on arrival, casting the bus into a cool shadow while the front faces glow white-hot. Radiators unfurl to dump the heat. A junior engineer suggests we call them space gills. The suggestion sticks because everyone is too tired to fight wit. The sample system must be bold, but not stupid. Touch and go is the phrase, but more like tap and sprint. The nucleus is a minefield of cliffs and vents, so the plan avoids landing. Instead, the craft flies through a chosen jet boundary, where pebble-sized particles slow in the rarefied gas. An articulated scoop snatches grains in a blink and shoves them into a cold locker that will hold them at a stubbornly low temperature. If we bring the dust home, it needs to arrive in the mood it left: no baking, no perfume. Now the headliners: microbeacons, a pocket orchestra of clocks, and reflectors the size of sports drink bottles. Each carries a tiny atomic timekeeper, an optical transponder, and a suite of sensors that care about only three things: when they are, where they are, and how the local medium complains about both. The beacons will be released in a string along the inbound leg, spaced so that some flirt with the time eddy while others skirt it. If the corridor dips the beat, the beacons should report a family of tiny disagreements that sketch the pothole's shape. It is physics by breadcrumb. But how do you keep a bottle alive in a blow dryer full of glass needles? The beacon chassis is printed from a ceramic composite that shrugs at heat spikes and scorns dust impacts. To orient without heavy reaction wheels, each beacon uses a magnetized fin that tries to align with the solar wind's magnetic field. It will not be perfect, which is fine. Perfection is not on the menu. Survival is. Communications forces a compromise between romance and reality. Deep space networks are busy and allergic to chaos, so the beacons will gossip among themselves first, using short laser links when geometry allows, forming a hopscotch chain that the main craft can interrogate in bursts. Each beacon stores data like a squirrel hoarding nuts in case it loses line of sight. The mothership then beams compressed summaries to Earth during scheduled windows, when pointing the high-gain antenna does not also point the heat shield into the furnace. Space is a relationship counselor. Communication matters, but timing is everything. Navigation earns a dedicated wall. Dust clouds mess with star trackers. So the bus learns a new trick, watching the polarization of scattered sunlight to infer the direction of the tail and the orientation of nearby hazards. When the polarization spikes, you are in a bad neighborhood. Guidance algorithms practice the equivalent of alley-oop maneuvers, dodging plumes using quick chemical puffs, while the ion engines hum their long song. In simulations, the craft looks like a dragonfly, ignoring a leaf blower. Meanwhile, procurement negotiates the universal constant of any mission: not enough money chasing too much ambition. The fix is a scavenger hunt through warehouses and partner agencies. An unused flight spare becomes the cold locker. A shelved star camera learns a new job as a dust watcher with a firmware patch. A student-built laser metrology package gets a seat at the grown-up table after surviving thermal vacuum tests with nothing but solder confidence. This is how space happens in a hurry. Repurpose, rewire, repeat. Testing squeezes months into weeks. A solar simulator roasts the shield until it sings. A plasma chamber blasts the beacons with fake wind, while tiny coils flip magnetic fields to see if the fins twitch as promised. A spin table whirls the bus until the control software throws up and then learns not to. The only way through an impossible schedule is merciless rehearsal. The coffee machine receives an honorary badge. Public affairs does its dance. A name, a patch, a tagline that sounds inspirational and makes no promises. The outreach team builds a web tool where you can adopt a beacon's nickname and track its vitals once deployed. A kid names one snooze button in honor of its obsession with time. Another is christened Breadcrumb 1, which is both accurate and adorable. There is a final meeting that feels like a cross between a wedding rehearsal and a heist briefing. The launch countdown sits on a screen, indifferent. Flight directors walk through the choreography. Boost, cruise, burn, shield, deploy, approach, corridor, beacon release, cadence, sampling sprint, and outbound pivot. Contingencies are stacked like dominoes, with labels such as dust tantrum and surprise flare. Nobody says good luck. In this business, you say, see ya on the other side. Engines light, the bus leaves the pad with the posture of someone politely exiting a crowded room. Days later, solar panels unfold like patient wings. The shade blooms into place, and the iron engines begin their steady whisper. On approach, the first 3 beacons wake, wink, and let go, tumbling into their own small destinies. Telemetry threads home, full of numbers that only a few thousand people on Earth find beautiful. Those people happen to be in charge. Ahead lies the corridor, where clocks get weird, and guidance will learn a new word. Next time, the bus noses into that neighborhood and discovers navigation with a split personality. Gravity's Practical Joke. Chapter 10, Gravity's Practical Joke. Gravity's Practical Joke. As the probe approaches, guidance systems report 2 slightly different gravitational pulls, a few milliseconds apart. The ship yawns between them like a confused pendulum. Pilots name the phenomenon déjà drag. The first hint is not the view, though the view is a charcoal snowball steaming in sunlight, but a twitch in the numbers that run the ship. Accelerometers are the nerves of a spacecraft. They feel every nudge from a thruster sip to a whisper of dust. Ours begin reporting a double tap. One tug, a blink, then another nearly identical tug. The timing offset is tiny, the way a heartbeat hiccups when you stand too fast. Guidance sees it as a split personality in the gravity vector and does what any responsible algorithm does. When reality forks, it politely panics. Normally, navigation fuses data like a diplomat. Star trackers tell us where we are pointing. Sun sensors keep the shield square to the furnace. Doppler from Earth gives a speed check. The inertial unit stitches it all into a smooth state estimate that says here, heading there, feeling this. Today, the fusion filter tries to sit on 2 chairs at once. One chair says the comet's mass is tugging a little harder than expected. The other says a little softer. The difference arrives staggered by milliseconds, as if the corridor itself is lagging while the ship is punctual. The plot looks like a tuning fork, drawn by an anxious violin. We test the boring explanations first, because boring is the most common genre in spaceflight. Is a reaction wheel burping? No. Wheels are steady. Are thrusters sneezing propellant droplets? No. Valves are clean. Is the star tracker being photobombed by dust glints and reporting a phantom roll that spills into the gravity solution? We narrow the tracker's field and mask bright specks. The fork stays. Somewhere, the universe snickers. Pilots give the glitch a nickname because that is how you tame fear. Déjà drag. It is half joke, half warning label. The craft feels as if it is trailing a pocket of syrup that catches up a blink late, then pulls again. Engineers dissect the sensation. One camp argues we are sampling 2 neighborhoods of the same gravitational field at slightly different times. because the corridor's time texture is not perfectly smooth. Another camp points at the plasma. The charged fog can tickle the craft with tiny electric forces in a rhythm that mimics a double gravity pulse. A third camp, the grizzled veterans, mutters that everything is real until proven otherwise and asks for more data. So we design a quick experiment, mid-flight. The bus carries two independent accelerometers on different mounts. We place them in a call and response routine. One listens while the other naps, then they switch. If the double tug is in the gravity, both will sing the same duet. If it is a local nuisance, like patch charging, the mounts may disagree. The result lands with the quiet joy of a solved crossword. Both see the same twin pull, and the offset matches the earlier readings. The ship is not glitching. Space is pitching two notes. Guidance adapts with a maneuver named in a meeting that had too much coffee and not enough mercy. Split-step navigation. Instead of steering toward a single predicted vector, the software carries two nearly identical futures in its head, each advanced by its own internal clock. At every cycle, it blends them with a weight that follows the fresher measurement. Think of walking on moving walkways that are almost the same speed. You keep a foot on each until the moment one proves itself. Then you shift your weight. The craft stops yawning and begins a precise wobble, like a tightrope walker who has decided to make it look difficult on purpose. Telecom joins the party. The radio link to Earth is a ruler made of light. Measure the minute changes in tone, and you can tell how fast the craft is falling toward the comet. We watch the tone ripple in sync with the accelerometer fork. The Earth side confirms we are being pulled in two beats that should be one. At the same time, laser pings to our micro-beacons start returning. With a quirk, a subset of beacons respond a hair earlier than geometry says they should, as if the space between bus and bottle has briefly shortened. Another subset drag their feet. The map of early and late returns sketches a faint lane that runs along the approach like a seam in an old road. Close to the nucleus, the shape of the culprit begins to emerge. The object is not a tidy sphere. It is a lumpy twin-lobed body with a narrow neck, the kind of shape that suggests either a gentle merger, long ago, or a snowman having a dramatic day. Lopsided mass can produce gravity fields with unexpected ridges and hollows. We would be thrilled to blame everything on that, but the timing offset refuses to fit a simple static field. It is not only where the mass is, it is when the pull is felt. We try an experiment born from a flight dynamics fever dream. We rotate the bus slowly while holding our path, letting the shield and radiators present different surfaces to the plasma. If charging forces are involved, the double tug should change with orientation. The fork barely budges. We then pulse a microthruster in the quiet space between taps. The next lagged pull arrives on schedule anyway. Gravity is doing its bit with comedic timing, and our stage directions are irrelevant. The mood on consoles settles into that slender place where worry becomes craft. The team tunes the filter to stop chasing ghosts and accept that the corridor will ring like this until we pass the tightest curve. They adjust thruster deadbands so the ship will not burn propellant, swatting every tiny oscillation. They prime the sample scoop for a pass that threads the region where early beacon returns cluster, on the theory that the seam in space is tied to vents we want to taste. This is the part of exploration that does not make posters. You learn to dance with an environment you did not design. There is a minor miracle in the numbers. The double tug fades when we slip behind a specific scarp on the nucleus, as if the local topography shadows us from the corridor's ripple. The team marks the spot. It is exactly where the next chapter's choreographed dive will happen. For a few minutes, guidance feels ordinary. The pilots exhale and make a note to celebrate later with snacks older than some missions. Space does not hand out clean victories, but it sometimes offers a breather. Behind the relief is a question large enough to ignore for only so long. If gravity can stutter here, what will it do to the material we snatch? Will the grains remember two beats the way our instruments did one? The answer is waiting in a cold locker we have not filled yet. Next time, we reach out with a scoop and bring home a problem that jiggles under a microscope. The sample that will not sit still. Chapter 11. The sample that won't sit still. The sample that won't sit still. Back on Earth, a captured grain jitters under the microscope, as if the laws of physics have the hiccups. When chilled, it calms. When warmed, it remembers a place it has not been yet. The lab fridge becomes a time therapist. The grain is smaller than a poppy seed and somehow louder, not in sound but in motion. Tiny, rhythmic nudges that show up as feathery blurs on high magnification videos. Technicians do the ritual. Isolate vibration, quiet the air, check that the microscope is not humming its own secret song. The table floats on cushions, the room sits inside a concrete womb, and still the speck dances like it is following a metronome only it can hear. Someone whispers that we brought home a jitterbug from the dawn of the solar system. Someone else whispers that if it starts beatboxing, we are leaving. Cooling is the first gentle intervention. The grain rides a sapphire stage into cryogenic temperatures, and the jitter eases the way a nervous foot stops tapping when the elevator doors open. Warm it by a few degrees. The motion resumes with the confidence of a show returning after intermission. It is not random. It has memory. The lab notebook gets a new column called Mood, because apparently we do meteorite psychology now. Under scanning probes, the surface reveals a city of ridges and glassy hollows. There are domains that look strained, like cooled taffy pulled too far, and kernels that look pristine, like frost that never met noon. When a nanoscale tip presses lightly, some strained patches relax in tiny jumps, as if the material stores flex the way a bookshelf stores dust. In material science, you see this in glasses and polymers that never quite settled into the lowest energy arrangement. The grain appears to be one of those eternal half yawns. It is not broken, it is uncommitted. Calorimetry turns up something odder. As the grain warms slowly, it releases little puffs of heat at specific temperatures, not enough to roast anything except old theories. Those puffs look like trapped configurations, flipping to more comfortable poses. Cool it again, and the puffs reappear at slightly different marks, like a stubborn instrument trying to tune itself, but trusting the wrong pitch pipe. That is memory in thermodynamics clothing. The sample is doing déjà vu with calories. A spectroscopist proposes a test that sounds like a dare to invisibility. Shine gentle light that excites only the most delicate bonds, then watch for delayed glimmers as trapped charges wander home. The grain obliges. After each illumination, a faint afterglow trickles out with a decay that should be smooth, but comes in steps. Those steps, likely map defects, acting as tiny waiting rooms. The pattern changes depending on the thermal history you give it, which means you can write and read a diary in this thing, one warm and cool cycle at a time. The grain is essentially an old tape recorder that never learned to erase. Then comes the magnetic flirtation. Some comets are rich in paramagnetic centers, unpaired spins that behave like tiny compass needles with commitment issues. We place the grain in a very quiet magnetic field and tickle it with radio pulses. The response looks like a chorus of needles that remember where they pointed last time and try to return to that angle even when the environment says otherwise. That is not mystical, it is spin relaxation. With a twist, pathways that have been opened once are easier to reopen. The lab's magnet earns the nickname therapist couch. We cannot resist a gravity joke. A microscale torsion pendulum measures whether the jitter could be driven by tiny electrostatic forces from the mounting surface. We swap substrates, gold, sapphire, diamond, and adjust surface charges. The dance persists. Whatever chat the grain is having is mostly internal, not a conversation with the furniture. To catch the motion without touching it, we turn to speckle interferometry, a method that turns light into a gossip columnist. Shine a coherent beam, and the reflected patchwork carries a fingerprint of surface microtremors. analyze the pattern over time, and you can see motions smaller than atoms climbing a staircase. The staircase has a rhythm. Every few seconds, a network of domains shifts in a coordinated wrinkle, then rests. It is like a city grid where traffic lights go green in waves. Except the traffic here is atoms dipping over tiny barriers, helped by the occasional nudge from trapped gas in pores releasing a breath. That trapped gas gets its own chapter in the medical chart. As we gently warm the grain, mass spectrometry on the surrounding vacuum sniffs trace releases, argon, neon, a whisper of methane, a sigh of carbon monoxide, written out as words, not symbols. Each release corresponds to a micro-jump inside the grain's structure. Pores unclog, microfractures adjust. The sample is a house settling, with creaks you can graph. In a moment of collective mischief, someone suggests we give the grain a little schedule shock. Heat pulse, cool pause, repeated with a spacing that does not match the obvious transitions. The idea is to see whether the grain can be taught a new rhythm. After several cycles, the speckle pattern begins to twitch in time with our imposed cadence. Not perfectly, but enough to say it learns. Stop the pulses, and the grain keeps that timing for a while, like a drummer tapping on a table long after the song ends. Memory is not only chemical, it is architectural. The triumphant narrative would end there, but the grain throws one last plot twist. After a night at a fixed cold temperature, the microscope catches a single decisive rearrangement. A fractured edge bows inward. A pit smooths, and the jitter baseline drops. The next warm cycle no longer provokes the same heat puffs. In other words, the grain resolved some of its long-held stress and moved on. One researcher sighs and says, therapy works. Another sighs louder and says we changed it just by caring. What does this add up to? A material that records the timing of its own strain and release, responsive to temperature, like a living thing to mood, and able to preserve that record across cycles unless you push it through a big reset. What at first looked like misbehavior now reads as a ledger. Which parts of the grain felt fierce sunlight, which hid in shadow? Which pockets held infant gas that kept the scaffolding propped? Which sections carried the memory of past passages so tightly that they trembled when we merely approached those conditions again? The sample will not sit still, because sitting still is not what it was built to do. It was built to remember by fidgeting. If you can coax memory from a speck under glass, maybe you can read memory from light at a distance. Next time, we step back to the telescope and watch the comet's brightness flicker like a metronome with a secret message, a modulation that counts more than time. Chapter 12, Message in the Brightness. Message in the brightness. Photometric analysis reveals a modulation in the tail brightness that encodes a repeating pattern, not language, more like a metronome that counts to a date. The counter points backward, then forward, then lands on now. The comet is keeping appointments. You do not expect a comet to tap on a wristwatch, yet that is what the light curve suggests. Photometry is stargazing turned into bookkeeping. Collect the glow, subtract the sky, subtract the instrument's mood, and see what is left. When teams plot the comet's brightness over many nights, a subtle pulse hides under the obvious rise and fall. It is not the quick heartbeat of rotation or the dramatic flare of event. It is a soft drum that keeps perfect time across different telescopes, like a band that never misses the downbeat. The first clue that this is not ordinary comes from color. Observers split the light into broad bands, one that loves dust, one that catches the breath of gases, one that mostly hears sunlight bouncing off grains. The pulse is present in each, but its shape changes in a way that feels intentional. Dust brightens first, gas follows a breath later. Scattered light stretches the tail glow a little longer. The order is consistent, as if a baton passes from one section of an orchestra to the next. If rotation were the only driver, the delay between sections would wander. It does not. Next, the team checks for geometry tricks. Sun angle matters. Tails perform differently when the line of sight makes them look thicker or thinner. So watch from different longitudes, different nights, different angles. The pulse holds its period like a lighthouse. Even when the overall brightness swells near the sun, the metronome rides on top, a ruler laid over a mountain range. There is humor in that. The universe throws a bonfire, and the comet still counts under its breath. Skeptics ask the right question. What if we are seeing interference from Earth's day, from schedules, from the human habit of sleeping? A network of small robotic telescopes steps in and does not sleep. They stagger their watch so that the light curve never blinks. The pulse keeps its spacing through the handoffs. It is not us. It is the object. Then comes the twist. Fold the light curve on that period, line up each cycle as if stacking sheets, and faint marks appear. Little deviations that drift from one cycle to the next. They are not random. They march steadily across the stack, reach the edge, and then reset, as though the comet added a page number. That drift is what makes the room lean forward. It means the pulse carries a second rhythm, a slow walk layered under the steady tick, like a second hand riding on the minute. To see what the second rhythm is pointing at, analysts try a trick from signal sleuthing. They slide a window along the data and measure how the period stretches or compresses with time. The stretch is not smooth. It changes slope at specific dates, forming gentle terraces. Terrace 1 aligns with a small increase in gas activity measured independently. Terrace 2 aligns with a change in polarization across the tail, a hint that dust grain sizes shifted. Terrace 3 lands with no obvious physical marker until someone overlays the predicted time of closest approach to the sun. The line settles right on it, like a compass needle finding north. Count the pulses backward from that terrace, and you get a tidy number that matches the days between earlier anomalies. Count forward, and you land on later, observing windows, where radio previews grew louder. The pulse acts like a scheduler that highlights milestones, not speech, not a code, but a calendar in light. The comet is not telling us anything. It is reminding itself. What mechanism could keep such tidy time? The leading suspect is a feedback loop between vents and sunlight. Imagine cavities that open and close as the nucleus turns, that lock into a rhythm when heated repeatedly, at nearly the same orbital phase. When the comet approaches the sun, those cavities do not simply vent harder. They begin earlier, nudge adjacent pockets, and create a cascade of micro outbursts that repeat every so many hours. Each cascade leaves a temporary highway of charged particles and grains that brighten the tail on cue. Stack enough cascades, and you get a drumbeat. Shift the temperature curve as the sun grows huge in the sky, and the drumbeat advances or retards by small amounts in a way that can point toward a special date. There is a second suspect, quieter but persuasive: structural relaxation. We saw in the lab that tiny domains can learn a cadence. Scale that up. Picture networks of pores in the nucleus that have been trained by many visits to heat and light. As the comet nears its tightest turn, a few networks switch their timing slightly earlier each cycle, a ratchet effect. Those small shifts echo into the tail as predictable brightening. When the orbit crosses the critical corridor, where time itself runs a hair slow, the ratchet locks for a few cycles, then unlocks as the comet leaves the furnace. That lock would create the terrace in the period map and anchor the count to a date. In other words, the bright tail is not broadcasting a message. It is keeping track. To test the calendar hypothesis, observers attempt a prediction that can fail. They forecast a modest brightening bump, a set number of cycles before perihelion, and call the night. When the data arrive, the bump is there within a sliver of a night. A second prediction aims at a quieter post-perihelion shoulder in the curve. That one shows up too. A little small, as if the comet almost forgot but checked its planner at the last minute. Scientists cheer softly. The comet remains dignified. One more check. Is the pattern only global, or does it slide along the tail like a wave? cameras with ridiculous dynamic range pick apart the tail into slices. The pulse travels outward as a moving crest, slow in the dust, quick in the charged ribbon, crossing fixed distances in times that line up with the period map. The metronome is not painted on. It flows. There is a superstition in labs and observatories that when nature reveals a rhythm, you owe it a question. We ask a big one. If a comet can keep time with itself so precisely, can it also keep time with space-time? Could those terraces be where the corridor's subtle dip nudged the cadence? That is a conversation for people who like roller coasters made of ideas. Next time, we pull up a chair for space-time itself and ask it to explain, in human metaphors, how a path can loop without breaking anything. An interview with a horizon. Chapter 13. Interview with a horizon. Interview with a horizon. Physicists explain closed time-like curves using roller coasters and spaghetti. The takeaway: small loops might exist without breaking the universe, provided you do not try to high-five yourself. The public sighs with relief and mild disappointment. Here is the key insight up front. Relativity does not give you a giant red button that says do not loop time. It gives you a very long terms and conditions document that says, under certain wild circumstances, paths through space-time can curve back to their own yesterday, without tearing logic, as long as the loop obeys local rules. Think of it like a theme park, where most tracks are gentle ovals, a few are intense corkscrews, and one rumored ride sends you past the same popcorn stand twice. The park's lawyers insist that you stay seated, keep your hands inside the car, and never touch your past self's soda. Start with the roller coaster. A closed, time-like curve is just a route where your clock keeps ticking forward while the route sneaks you back to an earlier event. You feel time moving normally on board. You never watch your watch run backward. The weird part is where you step off. If you disembark before you got on, you have a paradox buffet waiting. That is why the safety rules matter. The universe appears to have preferences that keep these loops tiny, localized, and very hard to exploit for drama. Great for physics, terrible for action movies. Now for the spaghetti. Space-time can be stretched and twisted by mass, by motion, and by pressure. Picture a pot of pasta as the fabric of reality, with strands that can be bent into knots. Most knots fall apart if you let go. A few tighten. In theory, certain extreme vortices around spinning black holes, along fantastically dense cosmic strings, inside exotic tunnels we call wormholes, can wind the strands so tightly that a path curls back. But every one of these options demands outlandish ingredients: gravity pushed to the edge, matter in temperaments we have never seen in the wild, or engineering feats on the scale of hubris. Nature keeps the good cookware on a high shelf. The first lifeguard on duty is called chronology protection, a polite way of saying the universe dislikes paradoxes and will raise the background fuss until your loop collapses into common sense. When theorists push their models toward loop formation, annoying things happen. Radiation piles up where the loop would close, pressure spikes, quantum jitters roar, and the would-be track buckles. It is as if reality clears its throat loudly enough to shake the blueprints out of your hands. You can sketch a loop on paper. Reality replies with a stack of permits stamped denied. Another guard is the energy bookkeeper. Many loop-friendly geometries require matter that behaves less like stone and more like negative push, bending space-time in a way that ordinary stuff refuses to do. We can produce tiny patches of such behavior in laboratories, but they are fragile, fleeting, and nowhere near the scale of holding a tunnel open against the weight of reality. It is like trying to prop open a vault door with a toothpick. The toothpick will write poetry about ambition. The vault door will close. So why are physicists willing to explain loops with a straight face and a spaghetti prop? Because even if nature never gifts us a walkable loop, the idea sharpens our tools. It forces precise thinking about cause and effect. It teaches us that time order can depend on the route you take. the same way the fastest path around a mountain might switch depending on weather. And it lets us ask cleverly designed questions. For instance, could there be tiny, harmless loops in esoteric regions, around horizons, or within intense vortices, so small and so brief that nothing macroscopic can exploit them, yet real enough that delicate clocks or fields would feel a nudge? The answer might be yes, and that is where the science gets interesting and the mischief gets house-trained. Public imagination understandably sprints to the grandfather problem. Physicists answer with the consistency principle, which is less about forbidding action and more about editing the script so that events that would break logic never happen. If you ride a loop, every attempt to create a contradiction is detoured by perfectly ordinary outcomes. A door jams, a phone dies, your past self chooses tea instead of coffee and leaves the cafe. The universe does not need a cosmic policeman. It needs boring probabilities, doing their quiet work until paradox starves. It is chaos theory with good manners. What about messages from the future? In most loop scenarios that do not cause ulcers, information cannot be amplified by bouncing through the loop repeatedly. You do not get a free megaphone. At best, you get a whisper that is already part of the history you remember. This is why physicists grimace when asked about lottery numbers. If you received a number, then you already did. The loop is not a shortcut to a different outcome. It is the meticulous weaving that ensures the same outcome holds together. Then there are horizons, those one-way curtains around compact objects. Near them, time and space trade hats. Paths that look innocent from far away turn acrobatic up close. You can thread needle-thin routes that circle the drain in wildly different ways. And in the math, some of those routes flirt with closed loops, but every practical attempt to ride them ends with the same guidance counselor talk. The forces are too strong, the light is too red, your atoms have other plans. Horizons give wonderful interviews, but terrible travel tips. So where does that leave our comet and its calendar tricks? Somewhere between the coaster and the kitchen. We do not need a grand, glamorous loop. We need the possibility that a corridor near the sun contains a small eddy that nudges phases and preserves rhythm, a looplet that cannot carry a tourist but can tap a beat into ice. That idea lives comfortably inside the safety rails. Clocks move forward, cause precedes effect locally, and no one high-fives their earlier self. The universe gets to keep its dignity. We get to keep our wonder. If you're disappointed that no one is cannonballing into yesterday, consider this. The most astonishing fact about time is not that it might loop in rare corners, but that it runs so steadily everywhere else that we build lives on it. That steadiness is the miracle. The loops are the footnotes that make the textbook more interesting. Next time, we trade theory for a bold hunch. What if a few icy bodies in our own backyard found a long-term shelter in these gentle eddies, time's quiet cul-de-sacs, and are now stepping out? Welcome to the Time Refuge Theory. Chapter 14, The Time Refuge Theory. The Time Refuge Theory. A daring proposal. Early in solar history, a family of icy bodies fell into a gentle temporal eddy near the sun, and occasionally re-emerge.
3I/Atlas is not visiting from elsewhere. It is returning from elsewhen, a local who took the scenic route through when. Picture the newborn solar system as a bustling construction site.
The sun is still learning to hold a steady shine. The inner regions are a kiln of light and wind, and a river of charged particles threads magnetic arches like glowing laundry lines. In that busy chaos, certain orbits around the young star are not smooth highways, but roundabouts with odd speed limits. The proposal on the table says a few small bodies wandered into one of these roundabouts, where time itself runs a touch slow, not by drama, just by dribble, and the architecture of light, heat, and gravity coaxed them to linger. They did not freeze in place. They circled in a cul-de-sac where their clocks kept a slightly different tempo from the neighborhood. The traffic sign reads, "Yield to chronology." What makes an eddy in time near a star that is otherwise an honest metronome, not a magic ingredient? several ordinary ones, stacked like pancakes. Gravity always sits at the base. Close to the sun, clocks tick a hair slower. Layer on top the shape of the path, which can tune how long an object hugs the hottest part of its loop. Stir in pressure from light and the wind of charged particles, which change how dust and gas depart a surface, and, in turn, how the object steers. Finally, add magnetic structure, the sun's habit of braiding fields into loops that shepherd charged grains and whisper to anything with a tail. None of these alone make a refuge. Together, and only for certain shapes and spins, they could build a neighborhood where the same patches of ice feel the same beat each pass and learn it by heart. The theory asks for a family, not a loner. These would be kin by habit, not by blood. Objects with close solar swoops that repeat a peculiar cadence. They might share favorite longitudes for their closest approaches, as if the eddy lives under a set of solar longitudes that return with the star's own slow rotation. They might also prefer certain tilts, aligning their poles so that the same vents face the furnace at the same phase, the way sunflowers keep a calendar with their necks. Over many loops, that stability lets surface layers grow stingy with change. They record the beat rather than erase it. A refuge is a memory palace disguised as an orbit. If that sounds soft, the tests are not. A time refuge family should leave fingerprints in the sky that you can check with a patient notebook. One prediction: their light curves, when folded on their rotation, should show little bunching episodes, only near the tightest swing, as if the drumline squeezes its pattern in the same bar every time. Another: their tails should develop repeated kinks at nearly the same places relative to the sun, not because the nucleus spins the same way, but because the corridor's fields do. A third: their chemistry should display stacks of ages in grains collected at different passes, with layers spaced like the family's orbital period, but with occasional offsets that rhyme across members. If two comets hum the same terrace into their light at the same solar longitude, you have more than coincidence. You have a neighborhood watch. Where did these citizens come from? Imagine early shuffles of material as the giant planets jostled outward and inward in slow dances. Icy bits that were nudged sunward would usually vaporize and fade. A lucky few entered paths that skimmed the inner fire and then escaped clean. Rarest of all were the ones whose shapes, spins, and vent geometries resonated with a patch of solar field that was just right. They learned the beat, settled into the cul-de-sac, and began the patient work of becoming clocks that did not know they were clocks. Why do they re-emerge? Because the refuge is not a vault, it is weather. The sun cycles, its magnetic quilt flips and frays, and the river of particles swells and slacks. Over centuries, the roundabout gains puddles, then dries. A refuge dweller that once felt a gentle inward tug might find the tug thinning, the beat loosening, the safe lane breaking into lanes that lead outward. The object steps off the carpet and arrives in our sky looking both familiar and out of place, like a neighbor back from a long walk that crossed several calendars. The theory is brave enough to be wrong and detailed enough to try. Teams have drafted a shopping list of evidence. First, a census of sungrazer candidates with absurdly good timing, checking for clustering in the angles of closest approach. Second, a patrol of polarization changes along their tails, looking for repeating features that stay glued to solar longitudes rather than to the comets themselves. Third, a search in meteor archives for showers that drift oddly against the calendar, as if their parent bodies kept a slow watch and shed at the same phase for centuries. Fourth, deep spectra that compare the fine structure of organics across visits. A refuge family should show similar stacks of thermal scars. There are pragmatic payoffs too. If you know a refuge exists, you can use its rhythm as a scaffold to plan missions that sip data at the best moments instead of guzzling at random. You can park tiny clocks on different sides of the corridor and let them report how time rolls across, not with philosophy, but with digits. Space exploration becomes less about racing a comet and more about mapping a neighborhood's tempo. And there is a human reason to like the idea. It reframes our visitor from a stranger to a local eccentric who has been living in a slow street off our main cosmic avenue. We are not being photobombed by the outside. We are being reintroduced to our own corner's quirks. The solar system turns out not to be a flat timetable, but a town with cul-de-sacs where nothing much happens quickly. And yet, over eras, everything changes. If there is a homeowners association, it has only one rule: do not kick the eddy. Should we interfere? Do we tag and tug these locals for convenience? Or let their odd clocks keep ticking? Curiosity pulls one way, caution another. That is where we go next. A round table on responsibility, risk and restraint in a neighborhood with wiggly time. The ethics of anachronism. Chapter 15, Ethics of Anachronism. Ethics of anachronism. Do we nudge it, tag it, or let it keep its strange commute? Philosophers, climate modelers, and historians share a table and a very large pot of tea. If time has neighborhoods, are we responsible for their zoning laws? The first key insight arrives before the kettle whistles. Calling something a refuge changes how we treat it. A refuge is not a resource to extract. It is a habitat to consider. If a comet's route includes a gentle eddy, where moments run slightly off the usual beat, then poking it is not just astronomy. It is urban planning with a cosmic HOA. The question is not, can we intervene, but should we file for permits with reality first? Bureaucracy is not fun, but paradox is worse paperwork. Around the table, the philosophers go first, because someone has to define the verbs. Nudge implies steering without rewriting identity. Tag implies observation that might alter behavior. Leave alone implies restraint that still changes things, because not acting while we are able to act is itself a choice with consequences. You can feel the room negotiating with language the way climbers test knots. If terms are sloppy, so will be the actions tied to them. Climate modelers add a sobering twist. Comets shed trails. Trails become meteor streams. Streams interact with atmospheres in small, cumulative ways. Change a comet's cadence, and you could shift the timing of dust encounters that ever so slightly influence high-altitude chemistry. No, not apocalypse. More like nudging the planet's calendar at the 5th decimal place. The world has enough surprises. If the best-case outcome of a push is better science, and the worst plausible outcome is a nudge to a system we barely balance, you reach for the pencil labeled caution, historians pour tea, and a perspective. We have a record of humanity meeting the unknown with nets and nameplates, then later regretting haste. Expedition journals glow with enthusiasm and footnotes filled with apologies. They ask us to remember that knowledge ages, but impacts linger. A temporal refuge, if that is what this corridor is, may be the rarest kind of archive. One that records not just material history, but timing. Tagging the shelves is tempting. Rearranging them is a genre of hubris with a long bibliography. Enter the ethicists with their favorite tool, analogies that itch. If a small rainforest teaches us the behavior of a climate, do we install weather stations in every clearing or set buffers where no boot prints are allowed? If an uncontacted village exists, our curiosity does not override the right to safety and continuity. The comet is not a person, but agency is not the only path to moral status. Unique processes can earn protection because the future would miss them if we bulldoze today. Conservation can apply to rhythms. The engineers clear their throats. What about beacons? Instruments are not neutral. Presence changes airflow, light, and mood. We can design to minimize disturbance, tiny mass, short lifetimes, trajectories that avoid shadowing vents. We can even make deployments reversible, like leaving flags that biodegrade in sunlight. Reversibility becomes a theme. If you cannot undo an experiment, maybe do a smaller one you can. Science does not need to be a bull in a cosmic china shop. It can be a polite guest who wipes their feet. Lawyers, because of course there are lawyers, point out that our current space treaties speak the language of non-contamination, planetary protection, and shared benefit, but they do not mention temporal preserves. A draft principle emerges in the room like a truce. Time-sensitive environments warrant added care. Before any action that might affect cadence or orbit, proponents must demonstrate that the intervention leaves a negligible imprint on the timing structure, not zero, negligible, and the burden of proof sits with the pushers, not the doubters. The phrase temporal stewardship gets written on a whiteboard in neat letters that all but glow. Indigenous scholars add a crucial chord: stewardship without listening is conquest with better branding. Many cultures hold stories where cycles, omens, and returnings structure memory. Invite those perspectives before finalizing any mission that would alter a recurring sky sign. A comet is not a deity, but it can be a ceremony, and ceremonies deserve respect. Outreach is not a press release. It is a seat at the table before the blueprints are inked. Economists ask their classic two questions: who pays and who benefits? If data from a paleoclock-class object can refine models that help protect satellites, crops, or health, then the benefit is broad. But if private firms monetize the timing by creating exclusive services, say premium forecasts of meteor microseasons, they inherit obligations to preserve the source. The rule is simple: if you profit from a rhythm, you help keep the drum intact. Then the room plays with edges. Could a gentle nudge be moral if it saves the comet from a fate that would erase the very timing we value, like a collision with a region of brutal heating? Maybe protective deflection earns an exception, but only when the evidence clears a high bar, and the method must be non-invasive, the cosmic equivalent of a lifeguard's whistle rather than a shove. The line between rescue and meddling is thin. We draw it with redundant checks and public eyes. Consent becomes the awkward guest. The object cannot sign a form. So consent refracts into proxies, consensus among scientific bodies, openness with the public, and built-in tripwires that halt an action if measurable harm appears. A mission might carry monitors whose very job is to veto the mission if the cadence shifts beyond agreed bounds. Imagine instruments empowered to tell their spacecraft no. That is not science fiction. That is ethics made firmware. There is also the matter of legacy. We are borrowing this neighborhood from descendants who will live with our footprints. The long tomorrow perspective says we design experiments so that someone born at a kitchen table a century from now can repeat, verify, and, if needed, reverse our steps. Data formats should be dull and durable. Archiving should be multilingual and lodged in more than one country. The future gets a spare key. By the last cup, the table finds a posture that feels like sanity. We will watch closely and touch lightly. We will prefer observations that ride the existing wind over actions that invent new gusts. If an intervention is proposed, it will be small, reversible, and supervised by metrics that measure not only success but harm. We will write a standard that treats temporal corridors as parks with rules. No loud engines. Pack out your trash. Take only light. Leave only a few photons. And we will keep room for wonder, because ethics without wonder calcifies, and wonder without ethics wanders. The comet will return, or not, on its own schedule. Our job is to be good neighbors on a street where minutes have moods. Next time, theory steps aside for choreography. The close solar swing approaches, and our choices turn into maneuvers. The perihelion standoff. Chapter 16. The perihelion standoff. The perihelion standoff. As 3I/Atlas curves toward the sun, the probe deploys the beacon chain. For a heartbeat, the beacons report 2 timestamps at once, then one wins. The tail brightens like a struck match. Every clock on Earth feels late by a thought. There is a particular silence in mission control that comes only when everything is loud elsewhere. Telemetry waterfalls scroll, nobody blinks. The probe, tucked behind its shimmering sunshade, slides along the inner rail of the orbit like a figure skater who decided the rink needed a lava pit. On cue, the payload door unzips. One by one, the micro beacons pop free and drift into their assigned slots, each a bottle with a heartbeat. They chirp their health, their pulse, their idea of now. For a few gorgeous seconds, those ideas do not agree. At first, the split is small, a few eye blinks of disagreement between neighboring devices. Then the corridor's character shows its teeth. Beacon 2 and Beacon 3 report twin time marks separated by a sliver, as if each carries two calendars and refuses to choose. The software on the mothership refuses to be dramatic. It stamps both, tags them as ambiguous, and keeps listening. A junior controller whispers, "They are double booked." The flight director does not look away from the screen. "Let it settle," they say, as if soothing weather. High above that whisper, the comet rounds the tightest turn. The coma shrinks and intensifies. The tail, thin and pale a night ago, flares. You can watch the brightening as a single number climbing, but better to watch the pattern spreading along the tail like a fast dye in water. A kink forms and races outward. Photons act like gossip. They carry the news faster than dust can move. The match has been struck, and the room tilts with a heat you cannot feel. Back at the chain, the schism collapses in an instant that feels longer than it is. The ambiguous stamps collapse to one choice. Every beacon flips to the same beat with the obedience of a choir, finding the conductor's eye. Later, the logs will show that the winning mark is the one that aligns with the corridor's predicted slow tick. The same beat our models feared and wanted. And the moment, all anyone notices is that the numbers breathe again. Pilots exhale like divers breaking surface. Then something strange washes across the ground network. Not a physical wave, a psychological one. Time servers do not drift, they are boring for a living. Yet analysts comparing intercontinental timing links report a microscopic phase hiccup in the comparisons that should be perfectly even. It is not a slip in the clocks. It is a slip in our faith, a measurable, harmless phase nudge in the dance between distant metronomes. If you were not watching, you would miss it. If you were, you felt late for a thought. The comet does not care about our metaphysics. It is busy being dramatic. Near the head of the tail, a bald, knife-bright spear appears, the charged ribbon snapping into alignment as magnetic lines reconnect and the newborn ions sprint along rails none of us can see. A broader, copper-toned fan blooms beside it as dust grains swell with reflected light. The two structures peel apart and then bend together again, like two pages in a book caught by the same breeze. Cameras saturate and recover. Software corrects. The star that hosts us looks very large and very close, which it is. Our probe now rides a blisteringly thin lane between sunlight and shadow. The sunshade glows white enough to make a poet squint. The bus behind it is a calm twilight. A cold storage drawer hums as the earlier scoop sample sleeps through the fireworks. The beacon chain, fanning out along the approach, takes its measurements with the stubborn patience of polite luggage. Their clocks compare notes. Some feel the dip more strongly, some hardly at all. The pattern sketches a shallow trough with soft shoulders. The pothole is not a hole so much as a sag in a well-worn carpet. If the corridor has a shape, it is a smile tipped sideways. A planned burn slides the probe through the seam where earlier returns came home a blink early. The guidance software performs its split step, weighting two futures and then leaning hard into the one the beacons prefer. Thrust is applied with the restraint of a surgeon. In the tightest heat, a vent on the nucleus wakes like a dragon with manners, sending a laminar plume that our cameras catch as a taut filament. Dust clacks against the shield with the sound of distant rain on a tent. The bus nods and keeps its promises. On Earth, observatories coordinate as if rehearsed. One set monitors polarization angles along the tail to catch the instant grains flip their alignment. Another times the brightness pulse that rides the charged spear. A radio array points ahead of the path, where yesterday's preview hum used to appear. And here's something new. An echo that begins at the same moment the beacons select their winner, as if the corridor itself chose a side and announced it. Twitter tries to name it in real time and predictably fails. Scientists keep their notebooks open and their jokes short. In the haze of heat, a gift arrives. Beacon 5, the most sunward of the lot, experiences a tiny phase lead that none of the others report. It is minuscule and would be lost in noise on a dull day. Today, it is a flag. The craft slews a fraction, framing that region in a narrow field spectrograph. The spectrum shows a fragile species usually bullied into silence near the sun, glowing proudly for a handful of minutes. Call it a souvenir from the eddy, a molecule freed by the same timing that chose the winning stamp. It vanishes as the plume rotates away, leaving gratitude and plots. The standoff ends not with a fanfare, but with a long breath. The tails match flare, steadies to a strong candle. The chain hums in unison. The probe arcs out of the worst glare into comparative sanity. Panels still intact, antenna still whispering, humans still pretending this is normal. The numbers say more than 1,000 press releases. During the tightest turn, the corridor nudged time's pace just enough to make precise devices quarrel and then agree, and the comet's own body answered by brightening in a rhythm it has practiced for a very long while. There will be committees and papers and arguments about how to define negligible when describing ripples in reality. For now, we have data by the gigabyte and a bus that did not melt. The standoff was not a duel. It was a handshake where both parties kept counting. Next time, the counting turns personal. As 3I/Atlas coasts away, the beacon string and the probe exchange a final packet from slightly different whens, and we learn what it means to send a message that arrives before it is sent. Homecoming, forward and back. Chapter 17. Homecoming, forward and back, homecoming, forward and back. Data pours in, a clear loop signature. The comet slips into its eddy, faint, proud, and a little frayed. We do not trap it, we learn its rhythm. The probe beams a final packet that arrives before it is sent, signed by the future version of itself. Paperwork is a nightmare, wonder is not. It begins like rain on a tin roof, pings from the beacon chain, steady, honest, and finally boring enough to trust. Stack those pings in time, and a pattern emerges that is not a circle and not a line, but something in between. A closed figure with a tiny offset each lap. Navigators call that a loop signature. Storytellers would call it a breadcrumb spiral that keeps finding its own footprints and adding a new scuff mark. However you name it, the shape says the corridor has a preferred beat, and the comet has learned the steps. As 3I orbits out of the furnace, the resonance softens but does not vanish. The last bars of a song linger in the air. The beacons sketch the geometry of the eddy like surveyors with very patient shoes. Those closest to the sun report the strongest phase sag, a little late on every lap. Outliers on the rim barely feel it. Thread through the center, and the effect flips sign for a heartbeat, as if the eddy has a calm eye where the tempo runs almost true. The map looks like a sideways smile with dimples, gentle, asymmetrical, and stable enough that the analysis team dares to use the word repeatable. In science, repeatable is a love letter. Meanwhile, the comet itself performs an exit routine that feels ritualistic. Brightness pulses widen, the tail's narrow spear relaxes, the dust fan fattens. Spectra show fragile species fade, while stubborn organics take the stage. Every change lands at a predictable phase in the orbit, as the eddy loses its grip. The message is clear. The loop is not a trap. It is a cul-de-sac. You glide in, circle on a slower beat, and glide out, carrying the memory, like a song stuck in your head. The nucleus looks a bit scuffed, like a traveler with a dented suitcase and a story. We had arguments ready about nets and tethers and brave ideas that age into bad ideas. We do none of them. The flight plan asks for humility. The bus makes a gentle plane change, not to corral, but to draft alongside at a respectful distance, a long blink of companionship before parting. It is the cosmic version of walking a friend to the train and not boarding. Then the packet arrives. It is small. That is the first surprise. After all this engineering, the future does not send a novel. It sends a postcard. Timestamps are tidy, signatures are tidy, and the headers say, in perfectly normal mission grammar, that the message is from our spacecraft, a few hours hence, relayed by Beacon 7, riding the inner edge. It should be impossible only if you ignore everything we just learned about local loops and consistency. On this street, it is merely impolite of causality to show off. The content is not instructions, not lottery numbers, not a confession. It is a check. Months before launch, the team agreed on a ritual in case this very thing ever happened. We seeded the onboard storage with a list of harmless challenges that no outsider could guess on schedule. If a packet ever arrived early, it had to include the correct next challenge response. A phrase assembled from data the craft would not generate until later. That way, we could tell the difference between a prank from noise and a message braided into the corridor's timing. The packet contains the right response down to the punctuation. It also contains a tiny delta for a thruster timing that the bus will command hours from now to shave a wisp of propellant on the outbound leg. Both facts become true later, exactly as the packet implies. The universe nods, as if to say, yes, I already knew you would ask. Engineers do what engineers do when reality winks. They verify to the point of melodrama. They cross-check clocks against multiple atomic standards, repass raw telemetry, simulate spoofing scenarios, and replay the ground software in a sandbox that is aggressively boring. The result is the same every time. The packet came early. It came from us. It did not change anything we were not already going to do. It is less a prophecy than a receipt printed before the purchase. Fate does not gloat, it itemizes. The emotional weather in the room fluctuates between giddy and reverent. A mission planner laughs once and covers their mouth, as if sound might scare the moment away. A guidance lead writes in the log with handwriting 2 shades neater than usual. Someone whispers that we have invented a new bureaucratic genre, the predated memo. The legal team will get their day. For now, we are busy being small under a large sky. Science, dutiful as ever, bends the wonder into work, with 2 copies of the same message separated by hours. One early, one on time. We can measure how the corridor treated each bit as it flowed. The early packet is slightly less noisy in certain fields, as if it took the smoother side lane we mapped near the eddy's eye. The on-time packet bears the tiny scuffs of a rougher path. Subtract one from the other, and a delicate fingerprint appears, the corridor's preferred channels. This is cartography at the level of seconds. From now on, any craft that needs to thread this neighborhood can step into the grooves we just traced with a postcard. As the comet's glow settles into ordinary, our bus swings to a departure attitude and begins the long, economical burn that will bring it home. The beacons continue to murmur until their tiny power reserves meet their tiny goodbyes. One by one, they wink out, a string of porch lights going dark as a town falls asleep. Beacon 7 lasts longest, as if honoring its cameo as a mail carrier for causality. When it finally falls silent, the spectrum of the region looks like any other hot, tidy solar wind. The eddy did not vanish. It simply became too faint for our instruments at this distance. Wonder went from foreground to background, which is where wonder usually lives. We package the data and the story for the world. The press kit avoids fireworks. It says, we measured a stable, local timing feature near a close solar pass. We mapped it with instruments that traveled with the comet, and we received a message that fit neatly inside the rules of cause and effect, while arriving in an order that made our eyebrows climb. The public will supply the poetry. The paperwork will supply the mild headache of filing a report, whose first exhibit is stamped tomorrow. Back at the comet, an empty lane glows faintly, where the match once flared. Our visitor recedes, edges softened by distance, carrying its practiced rhythm toward a long, private arc. We do not put a leash on it. We do something harder. We let it leave with its secrets mostly intact, and our curiosity louder than before. Exploration is not ownership. It is choreography with strangers. Next time, we come back to Earth and try the unglamorous miracle, living with calendars that might bend by a breath without losing our minds or our manners. How to live with wiggly time. Chapter 18, Aftermath. How to live with wiggly time. Aftermath. How to live with wiggly time. Calendars remain the same, but our stories change. We add a new category to our maps, locally time-bound. Kids draw loops on science fair posters. The last line of the mission report reads, "Next return window. Uncertain, but not unwelcome. Roll credits." And next episode teases the question, what else in our backyard took the long way through time? The first key insight is surprisingly domestic. Daily life does not implode when the universe admits to a few soft dents. Rent is still due, ovens still preheat, alarms still ring like energetic birds. But the background music shifts. News anchors learn to pronounce phrases like corridor sag and temporal eddy without flinching. Weather maps add a tiny corner box that tracks solar mood. Not because your picnic cares, but because satellites and power grids do. We used to treat space as a ceiling. Now it is a ceiling fan, and sometimes the pull chain rattles. Schools adapt with cheerful opportunism. Third graders build model comets with sugar and freezer burn, then label zones on the classroom solar system as slow street and fast lane. High schoolers run timing labs with cheap lasers and teach themselves the humility of measurement when their results disagree by a hair, and they learn that hairs are the point. College freshmen take a new elective called clocks in wild places. The final exam includes a polite essay question. If your watch is honest and the world is slightly wavy, who apologizes first? Museums redesign wings to hold wonder without hype. One hall features a long light strip that pulses at a steady beat, except near a glowing orb where the intervals squeeze by a breath. You can walk the strip, feel your steps sink, and when you reach the squeeze, you do not time travel, you smile. Another exhibit lets you send a message around a looped track where the delay subtly changes if you reconfigure the route. A volunteer explains that no causality was harmed in the making of this demonstration. People nod and take selfies with a sign that reads, "Please do not feed the paradox." Even paperwork evolves. Engineering standards insert fine print that treats time texture as a design environment. Instead of assuming the void is flat and obedient, spec sheets offer margins for brief, localized clock disagreements when missions skim dramatic neighborhoods. Insurance policies invent a rider called acts of rhythm. Lawyers claim they hate this, then secretly enjoy the novelty of clauses that define now with footnotes. Culture, which always listens from the next room, folds the discovery into art and jokes. A songwriter releases a track where the tempo tightens for one bar, and streaming services argue whether to flag it as a glitch or a feature. A novelist imagines a lighthouse keeper posted at the edge of the eddy, tending a beacon that ticks slightly slower in winter and slightly faster in spring. A cartoon frames a calendar with a loop drawn in crayon, captioned later is relative. The comments section debates whether the joke is funny. The discussion lasts exactly as long as these things always do. Scientists adopt two new habits: quiet confidence about what stays the same, and ritual patience about what does not. The first habit shows up in routine forecasts. Eclipses still on time, transits still crisp, spacecraft still rendezvousing with icy pebbles at absurd precision. The second habit shows up in release notes that say things like, "We accounted for local phase sags near the inner turn." That sentence is bland. It is also a tiny revolution. We have learned to carry a little flex in our models without equating flex with chaos. Think yoga for equations. In the streets, nothing dramatic happens, and that in itself is dramatic. People stop expecting cinematic time shenanigans in grocery aisles. They start noticing steadiness again, the miracle that clocks agree across continents most of the time. Steadiness is a dull hero until your phone's timing link hiccups for a blink, and you see your text jump one spot in a chat thread. You shrug and blame the eddy, the way previous generations blamed gremlins or Mercury being in an inconvenient mood. Every era invents a polite superstition. Ours just has better data. Policymakers convene roundtables that somehow include astronomers, electricians, and kindergarten teachers. Budgets shift by small, rational amounts toward monitoring. We lay another strand of fiber between timing centers, not because the old ones were wrong, but because redundancy is the grown-up form of optimism. A new international guideline suggests that operators who skim the inner solar lanes share timing signatures openly. The standard's title is a masterpiece of bureaucracy. Recommended practices for temporal neighborhood awareness. Engineers call it the good neighbor rule and go back to building things that work. There is an environmental angle too. Conservationists borrow the phrase locally time-bound and apply it to fragile, cyclical ecosystems that depend on seasonal rhythms. If a forest's insects emerge on a drumbeat and the climate shifts the percussion section, humans can play accompanist with lights and land use to help the melody survive. The comet's lesson refracts back to Earth. Rhythms can be protected, not just places. Some worries remain honest and small. Travelers ask whether flights that pass through certain latitudes will someday need timing advisories. The answer is a patient no, and also a reminder that your tray table should still be upright. Parents ask whether babies born during a strong solar cycle will be more likely to grow into night owls. The answer is charming folklore. Babies already run their own clocks. Traders ask if markets can exploit the eddy. Economists reply that if you cannot predict the scale better than a shrug, you are not exploiting anything. You are gambling with extra steps. Perhaps the sweetest change is personal. People begin keeping tiny rituals that honor time as more than digits. A baker sets a kitchen timer and, during the last minute, stands still to feel how long a minute is. A coder commits to closing the laptop when the sunset hits a particular window pane, not because the sky cares, but because their brain does. A bus driver pauses one extra breath at a stop where an old friend used to wave. These are not scientific responses. They are human ones. We learned the sky has gentle eddies. We answered by making our own gentleness. And the comet? Our visitor slides into the long hallway of distance. The ephemerides list a wide bracket for the next close pass and refuse to pretend certainty. The mission archive goes open access with a flourish that says, "This belongs to anyone who ever looked up." A small plaque on a control room wall sums it up with unfussy grace. Measured, not mastered. We keep the calendars, we change the stories, we add a category on maps that reminds future travelers to pack an extra dose of patience when skimming close to the fire. Somewhere a kid outlines a loop on cardboard and tapes it to a bicycle wheel, rides down the block, and declares themselves an eddy explorer. The neighbors clap because sometimes science is just another word for playing with better questions. Next up, we follow one of those questions into the hedges of our own backyard. If a comet could take the scenic route through when? What else nearby carries a quiet clock in its bones? Asteroids, rings, or dust belts that hum a rhythm we have not learned to hear yet?